The last time we sort of chatted, I kind of started a discussion. There are two things somehow that I reminded you of. You obviously had to know that last time. One was, of course, the importance of the gauge principle. So what we said, what we want to do, and this is the way we do physics, when you have a successful theory, we want to imitate it and see where it takes us. And it all started, we said, with QED. This is terrible, there is no good shock. We used to have good shock. It makes all the difference in the world. QED, which is based, we said, on a gauge principle. By the way, I'm not summing over the fermion. Obviously, any fermion here, any fermion in the world is here, right? Because the mu since here the information is hidden, remember. What I mean by Q, and I said I'm probably like everybody else, Q is just a diagonal, what we call the generator of U1 transformation. This is a diagonal matrix of charges, whatever particles we have in this world. So if you have a neutral particle, Q will be zero. So I can simply say every fermion is there, and then of course when it has a zero charge, it won't couple to a photon. And this had a symmetry, which we said psi goes into e to the I alpha. Let me be clear, alpha of x q psi f. And a mu goes into a mu plus 1 over e d mu alpha of x. Right, the celebrated gauge symmetry or gauge redundancy. The fact that because I have extra degrees of freedom, there will be a freedom itself in redefining the components so that I can arrive in two physical ones. The crucial thing, okay, there will be a lot of things you are going to be learning that more deeply. You had a course on QED, right? But not on the normalizability, I presume, right? You did a 3-level QED. Well, you will learn as we go along. What we said was really important here, out of all this sort of fuss, that you have, among other things, a well-defined propagator. For example, there is a psi equal 1, remember. I can write a propagator, but we wrote it anyway for the homework, right? In which the photon propagate takes the form, which is simply this one. And it has a manifest 1 over q squared behavior, free of any ambiguities, okay, well behaved. And it means when I compute loops, what is called, when I do perturbation theory, I can hope to get a finite answer. It's not enough, okay, it will take you some months to be able to prove that it actually happened, right? This is a great work of Schwinger, Feynman, Tomonaga that set the, if you wish, the tone, the framework, the cornerstone of modern field theory. It's hidden here. But you know, if I can achieve that the propagator is 1 over q squared, I can hope, and it has no ambiguities, I can hope that it will work. So this was important in trying to build a theory of weak interactions, okay? One was the gauge invariance based on QED, and the second thing was, I said, I couldn't overemphasize it, parity violation. Reminded you, 1956, by the end of the year, it was clear that parity is maximally violate. Remember when I polarized the neutron or the nucleus, cobalt, I found out that electrons were going in just one direction. So they have one chirality, right? Or if you wish, one helicity. Remember what we showed? Again, something that you have to know. that the helicity of left and right fermions when they are massless, of course, is well defined. Minus for left. So that's my definition of left from now on. If you wish, one of them is that the left-handed fermions have a helicity. Of course, it makes sense only for massless fermions, right? Because then I can define the helicity. Helicity, after all, is a projection of spin in the direction of motion. And that can be only defined for massless particles, right? Because massive particles sometimes move, sometimes don't, depends how you look at them, okay? So obviously there is no sense of talking of helicity of a massive particle, the same way that there is no sense of talking really of spin of a massless particle. It must be helicity, because you can't stop the crazy guy you get, right? There is something unreal about particles like photons that keep moving. So it was established that parity is maximally broken. In other words, that only left-handed fermions. So let's say that only, let me emphasize it, only left-handed fermions have weak interactions. What I mean, if I write the Fermi Theory, effective Hamiltonian, which is how it all started, right? A little history, as you remember, right? In 1930, Pauli suggested a neutrino. There is one guy that takes him seriously, called Fermi. You know, he couldn't get a paper published in Physical Review. Think of the irony. I tell you some interesting stories of the papers that couldn't be published as we go along. For example, everything that we do is based on quarks. Gell-Mann couldn't get the papers published of quarks in PRL. Got so angry that he never again published a paper in PRL. They regret it deeply. You know, he became so famous that they lost more than. So anyway, nobody else took it seriously, but Fermi actually said, well, I can write an effective theory. Just the way in QED I have an effective theory, current times current, right? When I propagate my photon, I mean, what is QED after all? It's an exchange of a messenger. And since A mu is hidden here, so in other words, this gives me an interaction, which is E, A mu, F bar, gamma mu, QF, right? But this is J mu. So I have an interaction which is current times the messengers. When I exchange it, right, what I will get. This is J mu here. This is J nu, right? Photon couples to J mu, J nu. But look at the propagator, for example, this gauge. I will get an effective interaction which is J mu electromagnetic, J mu electromagnetic times 1 over Q squared. Right, this is the propagator. Notice that it has to be one of the dimension of mass square. Why? How do I know that? You know, blindfold, without doing any calculation. How do I know that it had to be 1 over something that has a dimension of mass or energy? After all, in our units, mass, energy, everything is equal 1, right? So, well, this is my interaction, and it has a dimension, right? What is the dimension of an interaction, Lagrangian, Hamiltonian? I mean, action is, this is a definition of my interaction, say, of my Lagrangian. It's what I integrate to get an action. Action is dimensionless. This is dimensionful. And it has a dimension of m to the minus 4. So this has a dimension of m to the 4. But the current itself carries a dimension because why? Because fields carry dimensions. How do I know that they carry dimension? Because Lagrangian also has a kinetic energy, which is F bar, gamma mu d mu. And from here I see immediately the dimension of phi is in the units of mass. When I speak of a dimension, I'm going to use unit of mass always. Inverse of lambda.
3 over 2.
3 over 2. So the current has a dimension 3. Current times current has a dimension 6. So this got to be 1 over m squared. But photon mass is 0. So I didn't have to do any fancy thing, you know. In the end, if I have a massless messenger, I'm going to get 1 over q squared because there is no other scale. By the analogy then, we have a Fermi theory. Fermi said, why don't I write complete analogy for weak interactions? It will have dimensions 1 over mass. And that is, tell me how big it is? Well, it's something that we can write it as 1. It's often written as 1 over lambda Fermi square, by the way. Or m Fermi square, as you wish. Some scale square. How big is it?
1 over the mass of W squared. Sort of.
Right. It turns out a little bigger because when we write a W, there will be some small factors.
Yeah.
A little bigger. Well, good. Roughly. It's more like 300 GeV, it turns out. Lambda Fermi is roughly 300 GeV. So G Fermi, to remember it, is about 10 to the minus 5. GV2 minus 2, right? Agreed? This is what it has to be. And this is why people thought that weak interactions were weak. They thought that they were weak. Why? Because they used to exclude experiments when Q is small. But you and I know that weak interactions cannot be weak, because if I go to the energies when Q is large, there is nothing small about weak interactions, right? Remember that. The weak interactions are actually stronger, I will show you, than electromagnetic, funnily enough. They looked weak. Typical thing when you cannot, you know, probe the right distance, you won't have a clear picture of what is going on. So the parity violation, the fact that it's maximally broken, because after all we said under parity, phi L sort of goes into phi R. Strictly speaking, is there two components, right, which we did in the homework, they go one into each other. So if only left appears, that's the maximal breaking of parity. B breaking is maximum. And this is immediately 1957. Amazing, that period. Marshak and Sudarshan analyzed all the experiments. Actually, they suggest that some are wrong, and show that the form of the current has to be purely left-handed. But I can put it here, doesn't matter. So J mu, weak, would have the form. I emphasize it's left-handed. What form will it have? Help me here. You see what the photon does? It takes a particle into itself. We say that photon doesn't change flavor of a particle. Flavor is, for example, neutrino has a different flavor from electron. Fancy language that we use. An up quark has a different flavor from down quark. But the weak interaction has to change flavor, right? Because weak interaction is all about neutron decaying into electron plus nu bar. Or, for example, what else? What other process? You know, old-fashioned weak interaction decay, not more than they. What other decay, you know? Muon decay. Since we know that there are actually more generations. And en passant, I can say, you know, you must have noticed this before, this interesting thing, someone might have told you. There is this funny thing that somehow, when you look at the decay itself, that the lepton number is conserved. See, this is why I call it antineutrino. That's a convention that we've chosen. Okay? I can always do that as long as I don't find a neutrino. Then if I find a neutrino being different from antineutrino, I will say the lepton number is broken. Also the baryon number is preserved, right? These are both baryons. So what must be the form? Well, neutron must change into proton or up quark into down quark, so it has this form. And only left-handed. Oh, by the way I normalize, there should be a factor of 4. This is just definition of G-Fermi. There is a hidden factor of 4 because YL there is a projection and so on. Doesn't matter. It's a convention. It's a definition of G-Fermi, if you wish. There is nothing really truly fundamental. You see what you said, what Hassan said is that sort of it's the mass of the W boson. The real scale of weak interactions for you and me, something that is well defined physically, is the mass of a W boson. This Fermi scale depends how I normalize it. For example, I have a funny square root of 2. I didn't have to put that. Okay, here, this is history. So see, this is completely different from the photon. Photon couples to this. But F bar, gamma mu F, is FL bar, gamma mu FL. Plus FR bar, gamma mu FR. This is a 4-component interaction with both left and right enter, of course. That's one of the central results of QED, that parity is conserved. That's why they were so sure that parity was conserved until 1956, when this bombshell exploded. I'm going to try to be slow in the beginning. I have a problem that sometimes, I catch a fire and then I start being fast. I'm going to try to be slow, so use it to interrupt me, to ask anything, in the beginning. So now imagine that I want to imitate. And by the way, the attempt was made immediately. In 1957, already, Schwinger, one of the fathers of QED, wants to imitate QED for weak interaction. This is some years before the first standard model paper by Glashow. You remember when Glashow paper was written? No. You have any sense of history? Or it's so bloody far for you guys? It could be. I don't know from your perspective. I'm trying to remember probably. Did I really care when I was your age what happened, When Planck wrote his paper, but I had an idea when Planck wrote his paper. Oh, by the way, it did matter to me. I knew when Heisenberg wrote his paper and Dirac. You should have, these are extraordinary developments, that they should somehow be imprinted to you the way quantum mechanics is. You should have a feeling for the time that it takes, not so much when it happens, but how much time it takes to sort of see the theory evolve. Try to have that. I'll try to help you. So he says, I want to try to have a gauge theory of weak interactions. What could a gauge group be? I mean, you knew that it's all about groups. This, when I studied out, I guess Alexei told you, if not other people. Alexei must have mentioned this, right?
Yeah.
I think he should have written a covariant derivative and so on, or he didn't. He did?
I think so.
I often have contradictory statements from Alexei and the students. He tells me I did this, students often tell me that he didn't do that. I tend to trust him, forgive me. It's unlikely that he won't remember what he did. That can happen, So what should the group be? How do I know how to choose the group? What would be the logic? After all, here I started, and I forgot to say with U1. After all, this is U1 transformation, right? Call this U. As one generator, U1.
Somehow we know
Well,
the number of the mediating particles, then we can guess the number of that page group.
Yes and no. Because suppose that I have two mediating particles, then I can try U1 cross U1.
Yeah.
It's not that tricky. Now I want to do the theory of weak interactions only. Forget the photon, I'm saying. Let me try to do weak interactions. I can do U1 times U1. Can I do U1 times U1? What is the characteristic of U1? It's here. It's because of the fact that Q commutes with itself. See, the crucial thing is that the gauge boson corresponding to U1, in this case the photon, cannot carry charge. See, because U1, U1 only redefines the phase of the field. It's a very mild thing. So it's not just the number of generators. Although I agree with you, if I have more than one generator, most likely it won't be U1 cross U1, but I have to be sure. So there is another deeper thing. This is, however, changing the flavor. So it cannot be U1 times U1. It could have been, I don't know. There are two W's, so. If not, then, you know, it goes like, you know, the New York Times cartoon. About Einstein. There was a beautiful cartoon in New York Times many years ago. You see Einstein, you know, with his, and he's scribbling there. In a sense, when you do great new physics, when you think you are working on a fundamental issue, it's embarrassing how often trivial and simple it is. It's really almost like the cartoon there. That's what I want you to keep in mind. It's not what you have been told, that it's some baroque thing when you try to encompass everything, okay, into a mind-boggling complicated thing. This is absolutely wrong, the way it is often presented to you and young people. You know, Dirac will do this miraculous thing, but just trying to get an equation for a fast-moving electron. And he would really, you know, he would try to put the numbers and then it's not working. Then he says, I have to put this gamma, let me call it alpha and beta, then it turns to be a matrix, and so on and so forth, okay? This is interesting. So he really, developing the fundamental theories of nature, it turned out, he's sort of doing the thing, okay, you scratch your head, if it's not U1 cross U1, let me try SU2. Okay, so let's try. Let's try here. I want to strike you immediately today with the problems that we are going to encounter, so that you have a flavor. I'd like to have a picture. Of course, it may not matter to you, because a lot of you are interested in the formalism. If you're interested in the formalism, you don't care what you have to learn. You accept to learn it. For example, I thought I have this thing. I don't want to learn anything that I don't have to learn. So that's the way when I teach you, I want to show you that you have to learn something, really. And not just that you're learning, okay? So I try SU2. I can erase this SU nu. Let's just keep this for a moment. So in other words, just like in the case of having a messenger coupled to the, I would say that there is some W boson, let's call it W plus, so I couple it to the current, J mu. I didn't have to erase this. Well, I needed space. So I'll couple this to J mu L V, right? It's a plus charge because this carries minus charge. Agree? -1. The current itself. By the way, this coupling is called G over square root of 2. There is this funny thing about square root of 2, the way in weak interaction likes to be there. Just a convention. So this would be the analog. This would be the analog of A mu, J mu electromagnetic. This is this analogy. And Fermi was aware of this immediately. When he wrote his work, he knew that he could have written in this way. It's just he was premature. There was no sense to talk about something that you cannot probe. Because you see what you learn, this guy has to be very heavy. We are going to exchange a very heavy particle to get something, not to 1 over q squared. That I get when I get a massless particle. Remember, they were doing experiments at the MeV energies. And the mass of the W boson is roughly the scale of this. So he said there is no sense to talk about something. You know, this was the principle that would define modern physics from the times of Galileo. That you talk about the things that make sense, that can be probed in principle, that correspond to physical phenomena. Okay. What Newton coined nicely, natural philosophy. Physics is natural philosophy. Last person among great physicists that used this a lot was and is Weinberg. This term, maybe because Weinberg wanted to study philosophy, actually he wanted to be a philosopher. But fortunately, he became a physicist. By the way, it's interesting, okay, I have to, Pauli, besides being a great physicist, had a great sense of humor, very dry humor. Pauli is the guy who tells you you're not even wrong. So there is a nice anecdote. He has a bunch of his students and postdocs who are reading some paper of Einstein. And young people sometimes tend to be very sort of young lions, you know, when they are making it big, you know, to look down at the great people in the past. And they are sort of saying that the paper is stupid. It's nonsense. He says, wait. Einstein is not completely stupid. You know, you and I were taught, it's sort of interesting that when I tell you what it means to do actually physics as a precise science, to explain why Fermi doesn't want to talk about the W, because it makes no sense for him to talk about it. And in 1930, he doesn't even have a concept of gauge series that will emerge in the 50s, especially when you have to make it non-abelian. An interesting thing, for example, that we were always taught since we were little, that Newton introduced the principle of action at distance. That he didn't understand that there should be messengers with forces, right? The Newton theory of gravity is just the instantaneous force. That I presume you were taught also. Well, for example, that is wrong, among other things. Newton says literally that only a fool would believe that the force can be instantaneous. That would be crazy, he says. But I have no means of describing the messengers I believe that exist. So I will write the phenomenological theory, hoping that someone else does it. And this is what Fermi does. He leaves it open. If I want to have a particle that I cannot observe, remember, even in the 50s, the energies are very low still. We are coming close to GeV, but still below GeV. The reason that it makes sense to address the issue is because now you have a gauge principle, so maybe you can formulate something that will lead to new predictions, okay? So in order to get this, I have to get it from the gauge principle, and the gauge principle will tell me that the theory is SU2. What does it mean? It means that I have a certain doublet of states, which I can call U and D. Right? SU2 means that there is an upper-lower component that transforms as agree? Where U is It's unitary, so I can write it as E2 Hermitian. It's S determinant 1, so the generators must be traceless. And there are, of course, 3 of them that can be Hermitian and traceless. And this is sigma A over 2. I hate this chart. This is SU2. So this is the analogy with the U1 transformation. 1 generator, 3 generator, but the principle is the same. So if I want to write a gauge theory, I will have to substitute the ordinary derivative with the covariant one. How is it going to look?
Very similar.
Very similar. It's going to be d mu. So write for me, please. It's d mu minus I. I'm going to call the constant, I don't want to call it E. I call it G. And then what should I write?
Generator.
Sorry?
Generator.
The generator TA. No W. I'm writing SU2. There is no W. There are 3. No, I can't speak of W now. If I'm doing SU2, I will think about it later how to interpret it, okay? But I have 3 generators here. A, they have an index A. So I'm going to have, I can put the index where I want. Right, this is not the Lorentz index, upper lower. A goes from 1 to 3. This is obvious generalization of U1. This is what Yang and Mills did. They did it for general group, okay? And we will learn that. To do it for general group. You didn't do this in your group course on group theory?
In the course we didn't do it, yeah.
You did not?
In the course we did not do it, yeah.
We didn't do any physics. Just
Are you talking about
the group theory? Talk about the group theory.
Are you talking about the construction of Yang-Mills theory?
Well, just to write the SU2, doesn't have to be the whole of Yang-Mills. It's a sophisticated subject, but at least SU2. You didn't write SU2. Who taught the group theory?
Omar.
Okay. But you agree, this is obvious. I have to, of course, now I have to learn how to generalize this term, okay? But that will come later. Let's just focus on my covariant derivative here. So how it's going to look like? Let's still keep the Fermi theory. It's not so important anymore. We are going to get rid of it, or we'll try to recapture it later. So how will the interaction look like? So I will have this doublet. So the interaction is going to look like I, d bar, gamma mu. No, not d. Let me just twice to have u bar d, gamma mu, d mu, ud. Right, this will be the generalization of the term IF bar, gamma mu, d mu. You agree? So this is I, u bar, d bar, gamma mu, d mu. There is a kinetic energy. Of course, F2 symmetry tells me that there is no difference between up and down guys, right? It's just like spin. There is no difference between up and down spins when there is a spin symmetry, because I can rotate one and the other. They propagate the same way. I and minus I will cancel to give me G, u bar d, gamma mu, dA, a mu a, ud. So this is our interaction is hidden here, and it has the form which is, so this is G over 2, u bar d, bar gamma mu, and then I have A3, you agree, minus A3, A1 minus A, A2, A1 plus I, A2, mu, ud. Agree? G over 2, U bar gamma mu I didn't write this in a smart way. Let me rewrite it. Look, this diagonal piece, let me separate it. Diagonal piece is just sigma 3. I should keep it sigma 3. I don't get anything really, you know it. So let me write it like this. G T3 A mu 3. Let me keep it in a SU2 covariant form. So one term is U bar D bar gamma mu T3. I changed mine U bar D. But you see what it is, you know, T3 has Pauli matrix, so it goes with the opposite sign. But this is even nicer. The reason when I want to do it, notice T3 is diagonal. So H3 is very similar to the photon. It doesn't change flavor, right? After all, it will change up into up and down into down. So you can always write it in a kind of covariant manner. These other guys here are a little crazy. So now I'm going to write this G over 2 U bar gamma mu A1 minus IA2 mu D plus Hermitian conjugate. The other guy will have D bar, but we have A1 plus IA2. Okay? You check on my signs, you know, follow me, because notice I'm not looking at the notes, okay? And I will try never to look at the notes. I want you to be sort of participating and find the little errors that will definitely have to creep in. Let's try to continue. So let me introduce the following notation. Let me introduce the notation. W plus mu is A1 minus IA2 over square root of 2 mu. If I introduce that notation, notice that I reproduce the V current. This is the W boson. And the double boson has to be linear combination of A1 and A2 because it carries charge. The charged generator, as you know, is a linear combination of sigma 1 and sigma 2, the guy that takes up into down, okay, that we call sigma plus or sigma minus, okay, depending how we call it. Just remember that there is a minus sign here. Plus goes with the minus sign with our conventions. Why do I put the square root of 2? To maintain the normalization of my fields. I don't want to change it. I normalize A1, A2 in a certain manner, so I want to keep it. So actually I manage. So the beauty of SU2, you get a link interaction. That works. So you can be happy. See, 1957, by that time there was a Young-Mills theory. Schwingler knew of that work, that was 54, Young-Mills, so this could be done. So this becomes G over square root of 2. Now you notice the funny convention. It's convenient because I can write this U bar gamma mu D W mu plus. However, Marshak and Sudarshan, inspired by C. N. Yang and T. D. Lee, or better to say by the experiment of Madame Wu et al., tell you that this has to be left-handed. What would that mean? By the way, I don't know if I'm going to do it today, maybe not so important. There will be a highly non-trivial generalization of this transformation property, I agree. If I want to maintain gauge invariance, you have to look into it. Okay, this is what Yang and Mills did. Once we do that, everything else is going to follow. But that, let's keep for the time being. Okay, the Crux's issue. There's a beautiful essay by Weinberg about 10 years ago, which was called V minus A was the key. Weinberg in 2009. Sort of was reminiscing about the development of the standard model, and he was saying how essential was this V minus A. Okay, which we can emphasize. V minus A told you two things if you look at this current. Notice. It tells you that there is a sort of current which is vectorial in its nature, that there is gamma mu. It's not a tensor or a scalar. So when you see this, you can say, oh, now I can have a gauge boson mediating it. It's the same type of current that the photon has, except that it's parity violating. So what it really means, I'm going to have to erase this. When Salam, you know, when we wanted to have ICTP, he wanted to have, I think for him it was too important. We have three great things at ICTP. I used to come here in the 80s. The reason I'm here at ICTP, I fell in love in ICTP. I was working in the States, and I would come and I got invited by Salam in 82, and I would come and basically every year in the 80s to lecture in the summer school. And notice the blackboard of the, I feel like crying when I see these lecturers in the main hall not using the blackboard. It's the best blackboard in the world, literally. Because you can do the whole lecture without erasing anything. And you don't have to go up and down, you can just walk along and keep it. Another thing, he wanted to have the best library, physics library, and became the best physics library become more and more obsolete, right? We don't use libraries very much. The third thing was the bar. Kind of the ICTP bar is kind of special, right? It is sort of setting. Not irrelevant, by the way. If you want to do good physics, okay, you have to find a nice bar. When you want to think deeper. So, so really, how should this SU2 look like? I said it's a doublet when up and down transform, but it's actually not true the way I wrote it. Only left-handed guys transform under SU2. Because you have to transform under SU2 to fill this covariant derivative. Remember, I erase it. If you don't carry charge, you won't transform under U1. You have to carry the charge. So I can often use the language of charge. And it should be clear from the context. I can talk about SU2 charge. I mean the T3, for example. You know what I mean? The analog of electromagnetic charge. I may even use the word charges. I can mean generators. So in order to, from here, you get here. This is the connection. If you transform, you will fill the covariant derivative. So really the SU2, if I want to have the theory of weak interaction, it has to be like this. It has to be left-handed. What it means is the following. U and D up and down must transform under SU2. But what about the right-handed counterpart? Singlet. Must be singlet. True. So let me be clear once again. This means, so U and D left. I can say it like this then. Now I can generalize it. Fermion, every fermion's collection of fermions transform like this. Where my U is somewhere here. This is my U. The only thing I will say that TA, when it acts on left-handed fermions, is sigma A over 2, acting on left-handed fermions. That's what I mean. Whereas TA acting on right-handed fermions will be zero. That's what I mean by singlet. Serious. Because now we generalize SU2, right, to any representation, not just two-dimensional. I can have spin 77, whatever. Well, maybe not. What I have large component that just changes my TA. So these guys are singlets. And this is a doublet. Now you see that, you know, I don't know why I did it somehow. This is first time that I'm doing it. We usually do this later, but I decided I'll strike them in the very beginning. That you know why I have to do all kinds of gymnastics in order to build a standard model. Is that I would try SU2. The more general thing would, the simple thing would be, let me try SU2. Because inside SU2 there is this guy. So maybe this could be the photon. That would be beautiful. But it cannot be the photon, you agree? Because this guy couples to T3. But T3 has numbers like half and minus half. These are not the charges. The up and down charges, the charges electromagnetic for up and down is 2/3 minus 1/3 for quark, or 0 minus 1. I still have to say he wanted to know why I claim the neutrino is neutral with a good precision. Okay, we'll come to it, I think, shortly. So it cannot be T3. This is very different from T3. In other words, Q electromagnetic is not T3. It has to be outside. So you can say, oh, maybe I have a weak interaction theory. Why don't I try then? I'm sorry. You can say, well, try something. I don't know what's wrong here. Try, I think it's the Spremut. You can say, look, what will you do now? What to do? You give up. Schwinger gave up. Schwinger had a very good student who was not completely stupid. Glacial. Neither was Schwinger, but he stopped here. If you want to continue, you say, well, I have to add something. This doesn't work. SU2 doesn't work. I could try this. I could try now, just like Einstein. MA squared didn't work, so I try MB squared. Why don't we try this? Let me call it U1 electromagnetic. In other words, I have U1 outside SU2 that describes my photon. Can this work? By the way, in order to appreciate it, let me just then remind you, maybe it's not even clear what I mean by this. Although you may think that it's clear, but maybe it's not clear. What I mean by this is the following. So in other words, the generator of this would be Q, or Q electromagnetic. Sometimes I will call it Q, as if it's obvious. Sometimes I'll put electromagnetic. Okay. Now I want to be very careful. The definition of this is equivalent to saying that the generators of SU2 commute. This is the meaning of this. It means that U1 is not hidden inside, it's outside, so they commute. The same way that the generators of Lorentz group commute with SU3 color or SU2. And that's because of this commuting that when I speak of internal symmetries, I don't have to speak about Lorentz, because it commutes. I talk separately. And then I forget about internal symmetry. Is this possible? When I had the part of teaching the standard model, I want to do the following thing. The technical part I will teach you. But the standard model, you should be able, you must participate and help me build it. We should build the standard model and not read in the books. You have to understand how the structure emerged. In order to understand, you have to try to build it. You'll never understand by reading about it. So I'll pause a little bit until you tell me, is this possible or not? Sorry that I bug you. Maybe you don't want to think you want to just sort of sleep or think about other things, you know. Here I am pressing you. Who wanted you to be present, okay? By the way, one of the reasons that I didn't want to be recorded, I literally hate this room. And I remember that a lot of students hated the room. So before I decided to record it, we would actually have lectures in some nice sunny room, you know, for example, next door where there are beautiful windows. So you don't have to just stare at your teacher, you know, it's terrible on the blackboard. This is very important. There's a crux of the standard model is hidden here. How do I know whether this is possible or not? You see, if they commute with TA, that means that the electromagnetic charge cannot distinguish the particle. The photon would be flavor blind. The messenger associated with this charge will not distinguish up and down quarks because it commutes with SU2. It has nothing to do with SU2. By the way, if the photon does commute with SU3 of color, photon is colorblind. Photon doesn't care if you give him a red quark or a blue quark or a yellow quark. But he does distinguish between up and down, very much so. Look at this, okay, this guy is neutral. This would imply that there is no distinction between the particles in a doublet, because this guy would be outside. So this is impossible. This cannot work. So you see why, well, I still find it mind-boggling, and sometimes I'm happy about the atmosphere in our field. I feel that our field is called into some metaphysical, empty discussions, or why the numbers are what they are, or what not. In the it's very strange thing happened, okay? What happened in our field is very strange. I have to make a historical remark. In the early 80s, the standard model started emerging as a great winner in 83 W and Z bosons of out. It's just the beginning of the great, if you wish, triumph of field theory beyond U1. And yet 1 or 2 later, maybe 85, just a year and a half later, there is a proclamation that physics finished, okay? There is something that they call the string theory, and the claim by the fathers of the string theory, Witten especially, that there is nothing else to do, that the physics is finished, this is the final theory of nature, and so on and so forth. And we abandoned the field theory as the basic language. Very strange at the moment when it started to work. It reminds me of a letter that Max Born wrote in 1927. And the letter says, "My dear Werner, what a tragedy that physics is finished." Actually, he said that you and we finished physics. In 1927, Max Born tells Werner Heisenberg, what a tragedy physics is finished. They've done everything. There is nothing more to do. We just have to do more complicated atoms. Because there is something mind-boggling. After the great success of QED in the 50s, in the early 60s, there is a new movement, very similar to the movement of strings in the 60s, that preaches that the physics is dead as a fundamental science. It's called bootstrap repose. I don't know if you heard of these words. They are now in the dustbin of history. Bootstrap said that there is nothing fundamental. I'm made of Sergio, who is made out of Hassan. We are all made of each other. This is very funny, you know. At the time when triumph after triumph came in 64 quarks, in 1961, Glescher writes his paper. And I often worry, how come nobody noticed? How can you not see a beautiful paper that revolutionizes science? Okay? This is, imagine that Einstein writes his work, right? Newton does his work, and nobody notices for years. Glacier. 1967, Weinberg writes a paper. Well, he noticed the paper of Glacier, but nobody noticed this paper of Weinberg. Weinberg is famous by that time. He writes a paper, you should read that paper, please. Go back and read Weinberg. I'll send it to you to make sure that you try to read it. It's written the way a book would be written today. It's clear, it's crystal clear. And there were even, I think, that people couldn't notice this development because the prevailing mood was that there cannot be a fundamental theory of nature. So how can you see something that cannot exist? Sorry for this digression. That's why I want to do a little more than just teaching the standard model. I want you to appreciate what it means to do fundamental science. So Glacier says, well, if that doesn't work, that means that U1 has to be some other U1. And we call it hypercharge. It's not charge, it's some hypercharge. Right? What it means that it's true that TA will commute with this hypercharge. But what it implies for you and me, this is very important, that Q is T3. It must be a linear combination of the two, right? When I tell you that I have a gauge theory, all I'm telling you that the physics is inside my gauge group. So the photon must lie inside this gauge group. It must be one of the messengers. Here there are 3 messengers, you agree? Here there is 1 messenger, there are 4. One of them has to be a photon. But it's going to be a linear combination of the guys. Because it cannot be Y. White, it cannot be Y. Because then it would commute with EA and up and down quark will have the same charge. So it must be a linear combination that we write historically like this. This is what we call the electroweak theory. I hope you grasped it today. An attempt to make the gauge theory of weak interaction created immediately electroweak theory of weak interaction. Of both. Photon will be a linear combination of A3 and whatever I call this guy. A, say. After A, that would be A is mb squared. A is mb squared. Okay, good. Is this clear, please? This is what we call electroweak. Electroweak theory. And the crucial thing is parity violation. If parity had not been broken, things would look completely different because then these guys would be doublets and the whole thing would take another, you will see that as we go along more and more. Okay, the first striking thing is only left-handed guys are doublets. Okay, there is something crazy about this, right? Do you feel this? There is something crippled here. It seems that I was one of the rare people that, fortunately, when I read it, I'll tell you the exercise. I just started my PhD days when I was desperate because I hated this bootstrap and reciprocal. And I was saying, why the hell did I go into particle physics? What shall I do? And then I learned of this work of, so it's 1973, 74 when I started to do it, and I just learned of the work of Weinberg and at Hoft and so on, you know, and the whole, of course, light came through the tunnel and so on. But when I looked at this, I thought it was crippled. And it was very nice. The same Salam, who is one of the fathers of the standard model, felt some years later with Jogesh Patik, who used to come here visit in the summers, okay, they collaborated a lot. They also felt they cannot be that the world is so crippled. After all, there is something fundamental about left-right symmetry. But anyway, we'll come to it later. That's the way, this is the fact of life. Okay, so I can take care of this part. And this is why people got excited, by the way, later on in the 70s. Again, in the beginning, they ignored this paper completely. They have absolutely, glacier will have, it was so bad. This is really fantastic. In 1961, Glacial writes this paper. In 1964, Glacial writes a paper with Bjorken suggesting that there should be a charm core. They wanted to have some more symmetric world. There was already electron and muon and 2 neutrinos. So they said there could be a charm core. We'll talk about it a lot in the future, not today. You know, if you look at the 64 papers of Bjorken and Glacial, they don't cite Glacial. Glacial forget that he did this Glacial's work. It's very interesting. If nobody pays attention to you, you forget that you've done it here. You don't care. You don't think it's important. It was digged out. In 1967, Weinberg digs out the paper of Glacial. And immediately Glacial writes a paper on charm. You heard of this with Eliopoulos and Mayani. It's called Jim. You must have talked about that. Now he does this beautiful thing and shows you how it controls the phenomenology of weak interactions. It's very important to come back to it. Okay, I know that Alexei talked about it. But all of this will be ignored until early 1970s when Hoft showed that actually you can perform the same calculations as in QED. Then the world finally, you know, then they forget those crazy guys that said that physics is dead. If I can do the same calculations like Schwinger and Feynman, I'll sit down and do them. Okay, that's called the renormalizability. And what is great, what is very important, this is not just introducing some messengers. What Glacial then proves, there must be, besides the W plus, W minus, and the photon, there must be a false messenger, which we call the Z boson, and I will show you how the form of interaction follows from SU2 cross U1. It became a very predictive theory of new phenomena. So even if you're at energies, you can sometimes accept the physics that you cannot probe. If you can make predictions at low energies where you're doing your experiments, even if it's living here. It took them some time, you see. They had to wait in 1983 and so on. But there were clear predictions at low energies. And this is why, you know, everybody, including myself, you know, in 1974, it was clear that you should work on that because you could. Okay. The other thing, it was your homework. This was, you can see that the homework was just to make you, or remake you, get the familiarity with it left and right so that you can incorporate parity violation. Two things I wanted in the homework. Is pre-knowledge to follow the course, and of course to see what happens when the gauge boson is massive. Right? The Lagrangian becomes Broca. I can integrate this by part. Right? This is minus 1/2 d mu a nu. If I integrate this by part, this becomes 1/2, becomes a box a mu. There will be a box, right, if I integrate by part. But I have an m square here, so it becomes this. Minus d mu, d nu, a nu. The famous Broca Lagrangian looks almost like the QED Maxwell Lagrangian. Oh, sorry, QED, like Maxwell Lagrangian at the classical level at this point, except that there is MA. There are a number of things I can do here. One is find the propagator, but before I do that, I can immediately derive the equation of motion, which looks like this. And I can take another derivative here, d mu, and what will I learn?
Sorry?
I take a derivative here. The simplest way to do it, I don't know how you did it, I would take a derivative here again. I take the mu of this. What do I find out? That the box cancels. You notice? If I take the derivative here, maybe I want to take derivative d mu. Would be better, right? No, not d mu. This is a dummy index. No. Maybe it's not less stupid. What will happen? Can you see? Do I have to write? Or maybe you see after the homework? The box will cancel. This becomes the box. And then I find out that ma squared d mu a mu is equal to 0. This, of course, you wouldn't happen. You wouldn't see when ma is 0. This is the celebrated Procca result, which is now derived. It's not some gauge condition. Why? Because there is no gauge freedom. The way I wrote it, there is no gauge freedom whatsoever. Why the world should be? Well, there could be a little freedom. I'm going to think about it. There was some freedom. I wanted to use 4 coordinates a mu, but only 3 can be independent. This is a spin 1 particle. I can't talk of helicity now. It's spin 1. So that means that something, there must be a constraint, right? This is just telling you that 3 degrees of freedom of physics. And here is derived. It's not something that you impose. Those 3 degrees of freedom are don't worry if you haven't grasped everything here. All I wanted to see you that I had to mix electroweak. This, of course, will spend weeks on this. We'll come back to this and come back again. This is a spin 1 particle, and I can do it. I can stop this guy because it's massive. And then I can just construct the states, the Eigen States of spin. Remember the spin 1? I call them SA. You remember the structure constants itself provide a representation of a group?
Yeah.
In SU2, this is just epsilon. So, for example, T3 or S3, sure, I don't know now I wrote it, S3 is 0 minus I, 0, 0, 0, 0, 0, 0. This is a basis in which S3 is not diagonal. I can make it diagonal, right? Because now I find the Eigen States. And the Eigen States are the following: 1 plus or minus I0 with what eigenvalues? Plus or minus 1. Or this one, what eigenvalue? 0. Right? It should be obvious. It should be both familiar, but if not, it should be obvious. Okay, I have to just follow I have to finish the line of thought. So in other words, the polarization tensors, another thing what it tells me that when I go to, if I write that a mu of x is a Fourier of epsilon mu of p and minus CPX dp, then I have that epsilon mu, p mu is 0. Right, this is this condition. So I can write my polarization tensors for a massive gauge field at rest. I have epsilon, let me call them. What it means when it's at rest, it means that epsilon 0 is 0. If it is at rest. In other words, P is 0. So the polarization tensor would be the transverse ones would be 0, and then 1 plus or minus I, 0, and I normalize it 1 over square root of 2, just to keep the normalization. And then there is longitudinal guy, which I call, the name becomes clear when we boost it, which should be the one with spin 0. We can boost it then. I'll find out. I can compute this epsilon mu nu star I. There are 3 of them. I'm sorry, there are actually 2 of them. I could say 1 and 2. And this will be the 3rd one. I'll imagine, I'm calling a longitudinal, I'm going to boost it at some point in the z direction, okay? Just so the name will be. So this will remain, if I boost it, this will remain transverse, right? This won't change. If I boost it, this will remain in the xy direction, okay? You know what this is? You ever seen this, or you can compute it? It's minus g mu nu. Well, almost g mu nu. It's not g mu nu. For the photon, it will be g mu nu, with the usual conventions that we have. P nu over ma squared. Now, when I write this quadratic form, it's perfectly well defined. I can actually find the propagator by inverting it. And I hope that you all did it correctly. If you didn't, Visharit will do it for you. If there is some problem, we'll do it next time. Let me just write it at this point. And the delta mu nu, I don't know if you got it, is minus 1. Let me call it, okay, I call it p squared minus ma squared. G mu nu minus k mu minus p mu over ma squared.
Yeah.
Which is, notice, this is I over p squared minus ma squared sigma epsilon mu nu star over I. Notice something you would expect it physically. After all, what is a propagator? It's a propagation of the states that I have. And each of them looks like a scalar particle. It propagates it, except that it carries this tensorial structure in here. So by summing all of my states, I actually reproduce the propagator. And that's what you've done by homework, right? We got it here. The other day I went on for 10 minutes. I'll remember this. I'll give you back at some point, okay? But today, I can't do it today. I got to finish this line of thought. So far, so good. Except that I have a profound problem which kept people stuck for many, many years. It drove Weinberg crazy. He likes to say that, actually, when you talk to him, he often says that. You can look at the talk. He gave us a talk. This was a couple of years ago, and there was a sort of 50th years of the Standard Model 2-3 years ago, right, 67. I think maybe the talk was a little later. It doesn't matter. He gave him a talk for ICTP. It was a video talk. But a year later in Pasco's meeting, it was also a conference of the 50 years of the Standard Model, and he repeated this thing. He worked for years trying to renormalize the Standard Model, and he failed badly. Okay, a young genius called Hoft will come just as a beginning graduate student. He says that every time he does something stupid at home, he insists on something, his wife would say, "Shut up. You couldn't even renormalize your own bloody theory. Okay? You're a moron." That's what he says, so I can I can repeat it, okay? Now what drove Weinberg crazy? You can see it here. Look at the behavior of this propagator. When p squared goes to infinity, what happens? I have one piece which is good, but I have a piece which is not good. This goes in this limit to 1 over ma squared. I cannot get finite results. There is no way. Remember, the only way to get finite results, I have to integrate over something. Integral has to vanish at infinity. This guy doesn't want to vanish. I don't have to do a calculation for you. You can see that there is a profound problem. Two issues I have had to address. I will have to address. I keep addressing if I want to have the electroweak theory. One is how to put together the photon, which doesn't break parity, and W, which does. And it turned out, we said there will be some Baroque structures, okay? I'll come back to it. It seems that we'll be able to deal with that, the way Gleshow suggested. Here, this is much harder. I have a propagator that I've derived that doesn't work, but it's correct. There is nothing wrong with what I've done here. This is one of those moments when the change has to be dramatic and you have to accept it. So even as a lazy conservative person like me, there are moments where I told you I don't want to learn things that I don't have to learn. But it turned out this you have to learn what follows. It's called the Higgs Mechanism. In other words, we can't work like this. And it's strange that we'll solve it. Because whatever I do, whether I'm Higgs or whoever I am, it seems that there is an obstacle which is insurmountable. Because I can really derive it and the guy will be massive. A good propagator would be the one of a photon when I have a gauge symmetry. But I don't have a gauge symmetry because the guy is massive. So there is something highly non-trivial. I want you to appreciate there is a magic in the Higgs mechanism. And I have to spend some time teaching you the idea of spontaneous symmetry breaking. We have to break the symmetry without breaking it. This idea goes down to Nambu in 1960. That is what was called the Rochester Conference. Rochester Conference was a conference where all the physicists, the high energy, will get together. And it's held every 2 years. And now when you go to these conferences, I don't like to go there, there'll be more than 1,000 people. The first time in 1956, Marshak told me. Marshak was the president of City College where I got PhD, and I got to know him very well, because later on he wanted me to work in his place. He said the field was so small. You know, I was sort of saying the field grows. He says, don't complain. Let me tell you how big the field was. When he organized the first Rochester Conference in Rochester, that's why it's called Rochester Conference, in 1956, all the participants could stand in his living room because he had a party for the, what is today more than 1,000 people. You know, you see that the field that you enter and the field of the history we are talking about are rather different. Right? So Nambu gives this talk that maybe I can break symmetry spontaneously. And after the talk, it's very interesting to read the transcripts. Xin Yang, a great physicist, but a sort of tough guy who had very sort of clear picture, clear views, very strong. I got to know him very well. He was I worked for many years at Brookhaven Laboratory in Long Island, which is near Stony Brook University. He was at Stony Brook, and this was like CISA and ICTP. We had everything joined. And so Xin Yang was the kind of guy that always knew. I remember we would talk about football, and somehow he would talk as if he knew. And I'm a football fanatic, so he surely should have talked to me. So after the talk, he asked Nambu, are you saying that you somehow managed to break the symmetry? Yes. You can see Nambu picture, the guy got it. But I think you also said that somehow symmetry is not broken. Yeah, he says, Nambu, you got it. Well, let me explain to you, says Xin Yang, the logic. Things are either or not. So you understand, you can either break the symmetry or not break it. You understand that? Okay, so he goes on, and this is repeated 3 times. Spontaneous symmetry breaking is so strange that it's actually not broken. And Coleman used to call the hidden symmetry. That's what is going to be the subject of the course, if you wish, by and large. So they give this sense of drama. You can say, why be so excited, 60 years later? I'm still impressed by the magic of the Higgs Mechanism. Any questions on this? Yes.
For massive shapes, if you can derive, divergence of A equal to 0, but is there any way to derive it from massless case? From this technique?
No, because when MA is 0, if I take derivative, I will just get a 0. This cannot be true because I don't have to choose d mu a mu equal to 0.
Okay.
I don't have, it's not the following. I mean, it's a gauge condition that I impose. I have what we call, a light cone gauge. There are different gauges, okay? There is a Lorentz kind of gauge, Lorentz invariant. No, this is the freedom, because in the case of the photon, remember, actually I did something very different. And here is the expression is actually the central question that we have to face, and that Hoft understood. And that's the following. You see, when I worked with the massless photon, I have 2 degrees of freedom, but I worked with 4. Here I work with 4, but I have 3 physical degrees of freedom. The trick is, if I want to have this gauge freedom, I will have to introduce another degree. Either put it by hand, it will emerge in the case of Higgs. Okay, one has to understand that one can work with that, okay, or even invent it by hand. It's a comment when the time comes. But it couldn't be there. You see, there is the lack of this gauge redundancy in the way I wrote it, okay. Either I introduce another degree of freedom, in which case I will have the redundancy and then we'll have to fix the gauge, you will see that. Or it will have to follow here from the equations of motion, because this particle it's here, it's breaking this symmetry, right? This doesn't allow a mu going into a mu plus d mu, some theta of x, which are called 1 over e. It doesn't matter. The symmetry is not there anymore.
Have you worked a little bit on strings?
Sorry?
Have you ever worked a little bit on strings?
Well, I've read a lot, and I got very excited. Okay, maybe that's a question that we can maybe it's not an urgent question, we come to that. I got very excited. You see, the beauty of the strings that could be interesting for us is the world could have more than 3 or 4 dimensions, whatever, whether you speak of space or space-time. It's not clear what you mean by that, by the way. I don't know what you mean. What if you have a picture, what it means. By the way, there are only 3 dimensions. There are surely not more dimensions. And really it boils down at the end that we have a towers of states. But one way, strictly speaking, we could say maybe the other dimensions are compactified, little spheres. So there was a time when people thought that the only way to have this compactification, that instead of little sphere, you have something which is called Calabi-Yau manifold. I don't know if you ever heard of that. And there was something very interesting, the reason I got very excited. And the only way people thought that they knew how to do Calabi-Yau manifolds, I hope I'm not boring you, I mean, this is strictly not a lecture, is to take them as a algebraic duarities, whatever that means, or some complex projective spaces.
Toric varieties of some kind, I think.
Not toroidal, no. Calabi-Yau was at that time understood as a complex projective space with some constraint, algebraic. And a fellow called Candelas, a colleague of Weinberg in Texas, counted topologically different Calabi-Yau spaces. This was 1986, maybe, roughly, when this thing exploded. And he found out there are around 22,000 topologically. Now, you can maybe understand, or maybe you cannot. I'm not sure if you're getting that. If there is more than 3 dimensions, the number of generations that we have of fermions will have to do with the topology of the extra manifold. I mean, generations are like massless modes on this topology. If that doesn't sound right, who cares? Out of the 22,000, it turned out only one had 3 generations. This was around 85, 86 when I seen this, 86. And I left everything. This was so exciting to me. This seems to me, oh, this is wonderful. This now, maybe it makes sense. If after 22,000 only one has 3 generations, and it seems that we have 3 generations, there could be something there. So I worked for, actually, some time. What happened meanwhile? People learned that there are other ways of having this Calabi-Yau manifold, and actually infinitely many.
Yeah.
By the way, when you speak of compactification from extra dimensions, it's like finding a ground state. Physics is all about writing the Lagrangian, but equally important to find the ground state. If you don't know the ground state, forget it. And I think you know that we still don't know the ground state of QCD. There is a huge prize for whoever, you and I, would find the analytical ground state. So we do the Monte Carlo, very primitive Monte Carlo simulations on big computers. You know, that's not how you and I like to see things. Okay. One thing we share, whether you're interested in formal stuff or not, that we like to see analytically thing. Me too. I don't use a computer in my research. I need to see things written on a paper or blackboard. So there are infinitely many ways. Then people found out, Narayan came up with toroidal compactification. There is another infinity of ground. So now you're learning there is infinity of infinities or your vacuum states. It was clear that it was not a way to proceed to do science, okay? If it's hard sometimes with one manifold, so that's why I gave up. I came back to do particle physics, as it should be done.
I actually asked that question because you used the word light cone gauge, so I thought it probably you did strength gauge for some time.
No, light cone gauge people may use even, there are people who like to do that. So I worked on compactification that I did. Either we leave immediately, there was a question, I finished with this introduction. I can answer your question next time or today? We can do it next time. The charges you wanted to, I can.
I guess more like in an experimental way. But,
right, right. No, that's an important question. Okay. So the limit that I quoted, one thing I can do, I can probe the charge of electron and proton and see whether this sums to 0, you agree? Neutrality of atoms, that we can, that's easy to understand that we can probe that experimentally, right? Even celestial objects, even planets are extremely neutral, okay? When we say that they are extremely neutral, it means hydrogen atom is neutral. And its neutral really, charge of the proton plus charge of the electron is less than 10 to the minus 21 or something. It's less than 10 minus 20, let me see. I've seen 21, but let me see, this is for sure, conservatively speaking. So this is not surprising that you can do that. It will simultaneously tell you that the charge of the neutron is also very small. Otherwise, atoms wouldn't be neutral, and we wouldn't be neutral, you know, and there would be a huge electromagnetic force that will compete with gravity. So this you can get. How to get the limit on the neutrino is not that trivial, okay? Maybe that's what Sergei was asking, okay? You appreciate the question. Now, one thing I can do, when I cited that, maybe he was not completely honest, okay? Let me see if you will accept it. Suppose I say whether charge is conserved, conservation of charge. Conservation of charge. Now, not theoretically, but experimentally. So how do I probe conservation of charge? There are various ways of doing it. One is, for example, I look at the branching ratio for neutron decaying into proton plus neutrino plus anti-neutrino. Okay, I'm probing charge conservation.
Into electron present in neutrino.
No, I'm looking at the branching ratio. You know what the branching ratio means?
Yeah.
Decay rate divided by, so let me define it. This is a decay rate, neutron. It's okay, 3 more minutes? Let's answer it. Neutron goes into proton plus nu bar divided by gamma total. Gamma total really is gamma neutron going to proton, as Sergio was saying, plus E plus nu bar. This is the dominant decay rate. There may be other, suppressed 5, I don't know, I can have maybe extra neutrinos, okay, that's going to be very suppressed. So this is more or less. When people tell you that charge is conserved, that's what they mean. That the process is at Weyl charge. You even wanted to say, why am I looking into that? But in order to know whether charge is conserved, I have to study the charge breaking process and see how slow it is. This is less than 10 to the minus 27. Charge is extremely well conserved. Well, you can say in this process, you can say, well, you should convince me in all the possible processes in the world. Well, people look, for example, in the decay rate or a lifetime. You could look at the decay rate, for example. This is an interesting way to probe charge. Neutrino plus photon. So the lifetime for this is bigger than, you have some idea how good it is?
10 to the 24.
Very good.
Probably,
Yeah, I think it's a little bigger. I think it's 10 to the 26.
26, yeah, probably, yeah.
Okay, I'm impressed that you know this. 10 to the 26
From the particle physics course.
years. It's good to look at these numbers to get a feeling how good. By the way, we all believe the charge is conserved. But the limit is not as good as you think. For example, the proton lifetime is much better. Make a poll with the physicists. Very few of them believe that proton is really stable. Why? Because nothing happens if proton is unstable. No sacred law is violated. The second, their theories are predicted. More important than these limits, maybe for you and me, there is no way to write a theory with a broken charge. If you break charge, you find out that you cannot write QED theory as a perturbative theory of scatterings of electrons on electrons and photons. Everything diverges. So this is yet another reason why most of us believe that charge is conserved. The limits are very good. If you, of course, accept charge conservation, you get a fantastic limit from this process. Then the charge of neutrino has to be 0 to the same precision, because the conservation of charge is even stronger than the limits I have there. If you accept charge conservation, you get immediately from these two, you will get that Q nu is less than 10 to the minus 20. I don't know if you want to continue being a devil's advocate, say, well, I don't want to accept it. Maybe there is some process that violates charge. Then there are people that try to put direct limits. For example, what would happen if neutrino was charged? In the sun, it will be produced from the photon in the sun is like a plasmon, what we have. It behaves as it has a mass because of the temperature. When you put a photon in a very hot medium, it effectively gets a mass. It behaves. So it can decay into a neutrino and antineutrino if they carry charge. And you will produce more neutrinos. The photons will be cooling off. But sun keeps shining. Yesterday didn't look so convincing, but look out. So from the fact that sun keeps shining, you can put a limit on the charge of neutrino less than about 10 to the minus 13. And there are even some limits directly from experiment, okay, that I haven't studied really. You look at the scattering and try to find what will happen, okay. I can't speak with any authority there. I can dig it up. Those limits are not as good. Laboratory limits are about 10 to the minus 10. But I think they are good enough that for the sake of this course, you and I can go on. assuming the neutrino is neutral. Nothing would, how to say, no, that's not what I want to say. I have to assume the conservation of charge because I can't construct a theory that violates charge. I will remind you of the things that may not be zero, like photon mass. Nothing goes wrong if photon gets a mass, by the way. Photon is neutral. I don't have to break charge a priori to give photon a mass. We can come back to that question. And I can be open-minded. I will pretend the photon is massless because the limits are pretty good, but nothing will go wrong. I would immediately know how to deal with that. I don't know how to incorporate the theory with charge convecting, therefore for me neutrino is neutral. To the precision that I hope would satisfy. Okay.